Okay, up to this point, you've been told that this column wants to lose one electron, thereby becoming positively charged, um, typically a +1 ion. And you've been told other stuff like these elements want to be +2 and +3 and -3 and -2 and -1. But you don't really have a satisfying answer about why these numbers are the way they are. So I'm making this video for the kids who have that question. They want to know a little bit more about why these numbers are the numbers that they are. So to show you this, I need to show you a drawing, and don't be intimidated. We're not going to get into depth with this, but this drawing shows something called orbitals. So this thing right here, this is an orbital, and so is this thing and that thing. All these things are orbitals. Now, what is an orbital? An orbital is where the electrons are. So the electrons of an atom are whizzing around in these orbitals, in these locations, and that's how we describe their location. And there are rules about orbitals. One of the rules is that each orbital can hold 2 electrons. And believe it or not, just by getting that little tidbit that each orbital can hold 2 electrons, so you could put 2 electrons in here, 2 in there, 2 in there, 2 in there. You could put 2 electrons in these orbitals. We actually already know something fundamental about the periodic table. And to show you that, I need to drag a periodic table in. Okay, that's the best I can do with the room that I've got. But just by knowing that each of these orbitals can hold 2 electrons, that explains why this first period on the table only has 2 atoms in it. So hydrogen and helium occupy that first period because hydrogen has 1 electron, and that halfway fills this orbital. And then helium has 2 electrons, and that fills this orbital up the rest of the way. So the electrons in here are whizzing around, and in a hydrogen atom there's only 1, and he takes up half the space. And then in helium there's 2 electrons, and he fills it up the rest of the way. So what if we went to element number 3, like lithium? Well, you would need a bigger sphere because this sphere is already filled with its 2 electrons. So as you go down the table, these spheres just keep getting bigger and bigger. And that explains then why this part of the periodic table is 2 atoms wide, because this spherical orbital can hold 2 electrons. And that's also, just in case you were wondering, that's also why helium in some periodic tables, you might see helium over here. You don't see it in this place too often, but you might see that. The reason why we usually put helium over here is because it has another special property that we'll talk about in a minute. Okay. So let's go to some new orbitals. Let's go to these guys right here. These are called the p orbitals. And each one of these can hold 2 electrons, so that's a total of 6. So what does that explain? That explains why this part of the periodic table is 6 blocks wide, or 6 atoms wide. This is called the p block. Not that we care in this class, but anyway. And then this next bunch down here is how wide? It's 1, 2, 3, 4, 5 orbitals wide. Well, that explains why this part of the table is 10 atoms wide. And this is called the d block. All right. And then right down here, we've got the f block. 1, 2, 3, 4, 5, 6. There's 7 orbitals. Well, guess how wide the f block is? Yes, it is 14 atoms wide. Okay, so that's why the periodic table has the shape that it has. So I promised to talk about why these atoms do what they do chemically, why some want to become positive, 1 or 2 or 3 or whatever, and why some want to become negative. And I think the best place to start is with this group right here. These guys are called the noble gases. So-called noble because they don't associate with other atoms very much. So something about the noble gases makes them stable. And if you are stable, you don't really care to react chemically with anybody else. So these guys, why are they stable? Well, that's because their outer orbital is full of electrons. So their outer orbital is full. So what's so nice about having a full outer orbital? Why is that stable? Well, it has to do with energy. Things in the universe seem to crave less energy. For example, you don't see rocks rolling up hills; you see rocks rolling down hills. Just as an analogy that I like to think of it, I like to think of it like this: like this guy has remote control cars, and he's got this little wheel balancer. So this wheel is spinning, and it's all just sitting there spinning really nicely because he has balanced the wheel. If we drag this out to, I think, 114 or so, he shows us that he has put like putty in there. Yeah, he's put some putty inside the wheel to balance it. But if he takes an unbalanced wheel and puts it on his little balancing stand and gives it a spin, watch what this stand does. It vibrates across the table. It shakes across the table. Maybe you have seen like cars going down the road and they've got a bouncy wheel, or you can feel the shake in your car. Well, it's because I liken it to the orbitals. I kind of think of it like if you were an atom and you didn't have a full outer orbital, you'd love to get that outer orbital full so you could be more stable. So where I'm going to go next is I'm going to go to the next group over that is, I guess you could say, kind of jealous of the noble gases. Let's go to this group. These guys are called the halogens. So these guys are one electron short of a full outer orbital. So what would they like to do? If I were fluorine, what I would like to do is I would like to gain one electron, and I would like to be like neon. I'd like to be like this guy. So that's why these guys want to gain one electron. So let's jump back over here to lithium. What's lithium's problem? Well, you might think lithium has a huge problem, because if lithium wanted to be like neon way over here, lithium would have to gain 1, 2, 3, 4, 5, 6, 7 electrons. Well, lithium can gain 7, or it can lose 1 electron. So that's the low energy choice. The easier choice is to lose 1 electron. So if lithium loses 1 electron, he becomes like helium, and then he has his outer level full, which is the level that has only 2 electrons in it. So that explains why all the metals on the table, they all want to lose electrons and therefore become positive. It also explains why these atoms that are really close to the noble gases, the nonmetals, they want to gain electrons to become stable. So then we can use this predictability. We can say, okay, so oxygen is right here, and what can it do? Well, if it gained 2 more electrons, then it would be stable. So that's why oxygen likes to become a -2. So you can look into this if you want to and discover lots more stuff about why the atoms bond the way they bond.